All measuring devices, balances, pipettes, thermometers, and so forth, are made to limited specifications, and we use our imperfect senses and skills to read them. Therefore, we can never measure a quantity exactly. Put another way, every measurement includes some uncertainty. The rightmost digit of any quantity that we measure is always considered an estimated digit. So let's say we had a number like this. Let's say we had 2.36 milliliters. We can make the assumption that the rightmost digit, the digit farthest to the right, is an estimated digit. Let's try another example. Let's say we were measuring something that weighed, 23.41 or 431 kilograms. The rightmost digit here is the number 1, and so again we would assume that that is the estimated digit. When we write down a measurement, the recorded digits, both certain and uncertain, are called significant figures. And so the 2.36 milliliters, since we have three numbers, two of them are certain, the 2 and the 3, and the 6 is uncertain, but again, the recorded digits, both certain and uncertain, are called significant figures. And so 2.36 would have a total of 3 significant figures, which I'm going to abbreviate SF. The measurement 23.431 kilograms has 4 numbers that are certain. We have 1 digit that's uncertain, but again, we put them all together and we get all of the significant figures, and we have a total of 5 significant figures in this number. The greater the number of significant figures in a quantity, the greater its certainty. Here's an example where we're measuring the same temperature but with different thermometers, and thus we produce results with different amounts of certainty. You can see the thermometer on the left has graduated increments of 0.1 degrees Celsius, but the thermometer on the right has graduated increments in 1 degree Celsius. And the way that we get this temperature reading, 32.33 degrees Celsius, is that we estimate 1 digit past the smallest calibration. Now let's take a look at the calibration or the increments on this thermometer. We have 32, we have 32.1, 32.2, 32.3, 32.4, 32.5, so on and so forth. And you can see that it's above the 1, 2, 3, right? The meniscus or the top is above 32.1, 2, 3, just slightly, okay? And the estimation made by the reader using their eyeball at the same level of the meniscus is that they're saying, well, it looks like it's about a third of the way up between these two lines right here. And so they're estimating that digit at the hundredths place as being 0.03. So we get 32.33 degrees Celsius. On the thermometer on the right, we have gradations of 1 degree Celsius. So we have 31, 32, 33, 34, 35. So already you can see why we have less certainty, because we have the same temperature, but when we read it, the smallest increments, again, are 0.1 degrees Celsius, and you can see that it's above 31, 32, so it looks like it's around 32.3, right? So the reader reads from the top of the meniscus and sees 32.3 degrees Celsius. So the take-home message is that the measurement on the left is known with more certainty because it has more significant figures. 32.33 degrees Celsius has 4 significant figures, and 32.3 only has 3 significant figures. When you take a measurement or use one in a calculation, you must know the number of digits that are significant. All digits are significant except zeros that are used only to position a decimal point. So sometimes I call those leading zeros. So let's say we had the number 2.033. There is a 0 in the number, but it's not used to position a decimal point. It's sandwiched in between two non-zeros. And so this number has a total of 4 significant figures. If I had the number 0.000562, the zeros at the beginning of the number, we call these, again, I like to call these leading zeros. These are only used to position the decimal point right here. And so none of those zeros that I have underlined are significant. And so this number has a total of 3 significant figures. A complication can arise when zeros end a number. Now, zeros that end a number are significant whether they occur before or after a decimal point, as long as a decimal point is present. Let's take a look at these examples here. 1.030 milliliters has 4 significant figures because both of the zeros come after a decimal point. 5,300 with a decimal liters has 4 significant figures. And the reason why is because although those 2 zeros are at the end of the number, there is a decimal point present. And so that renders all of the zeros significant. It gets a little bit interesting if there's no decimal point at all. Zeros at the end of a number are not significant. So if we have 53,000 liters but we have no decimal point, we only consider the non-zeros to be significant. And so this number has 2 significant figures. Just as an FYI, however, we can express this number to 4, 3, or 2 significant figures by using scientific notation. For example, if you expressed this number as 5.3 times 10 to the power of 3 liters, then we would say we've got 2 significant figures. If you express this number as 5.30 times 10 to the 3 liters, then we would have a total of 3 significant figures. Now, to express it with 4 significant figures, we could either put a decimal point at the end of it, just like shown right here, or we could write it in scientific notation as 5.300 times 10 to the 3 liters, like that. With that in mind, let's try a problem. It says for each of the following quantities, underline the zeros that are significant figures and determine the number of significant figures in each quantity. For D to F, express each in exponential notation first. Exponential notation is the same thing as scientific notation. Let's start with A. We have 0.0030 liters. The leading zeros are not significant because they're simply used as a placeholder for the decimal place, but the 0 at the end of the number is significant because it comes after the decimal place. And so this number has a total of 2 significant figures. If we look at the second one, B, 0.1044 grams, the leading zero here, that is not significant, but the 0 after the decimal place is significant. And so this number has a total of 4 significant figures. We have 53,069 milliliters. The 0 here is significant. We have no decimal place, but that 0 falls in between non-zeros, and so it is significant. And so we have a total of 5 significant figures here. The next ones I've gone ahead and I've already expressed them in scientific notation. And just to help you with that, if you're unsure how I converted this number, 0.00004715 meters, into scientific notation. Well, since the number is less than 1, I just moved the decimal place 1, 2, 3, 4, 5 places to the right, and so I put 4.715 times 10 to the negative 5 meters. Again, all of those leading zeros are not significant, and so this number has a total of 4 significant figures. The next one, 57,600 decimal seconds. I've already gone ahead and expressed that in scientific notation. We have zeros at the end of a number, but we do have a decimal point, and so those are significant figures. And so this number has a total of 5 significant figures. And then we have this number at the end. I'm not even going to bother reading all those zeros because those are all insignificant, all those leading zeros at the beginning. But the trailing 0 is significant. And so this number has a total of 4 significant figures. The rules that we use for significant figures in calculations are as such. For multiplication and division, the answer will contain the same number of significant figures as there are in the measurement with the fewest significant figures. So if we had to multiply all of these numbers, 9.2 centimeters by 6.8 centimeters by 0.3744 centimeters, it's pretty easy to punch that into your calculator and you get this big number, 23.4255 centimeters cubed. Well, you can see that the answer that's in bold here says only 23 centimeters cubed. Now, how did I arrive at that answer? Well, that answer has the correct number of significant figures because if I look at each one of these measurements, 9.2 centimeters has 2 significant figures. 6.8 centimeters also has 2 significant figures, but this measurement here, 0.3744, has 4 significant figures. Now take a look at the rule. It says that the answer has to contain the same number of significant figures as there are in the measurement with the fewest significant figures. Which number has the fewest? Well, there's a tie, okay? Both 9.2 centimeters and 6.8 have 2 significant figures, and therefore our final answer, when we round it off, can only have 2 significant figures. For addition and subtraction, the answer has the same number of decimal places as there are in the measurement with the fewest decimal places. Let's take a look at an example. If I want to add up these two volumes here, 83.5 and 23.28 milliliters. Again, pretty easy to punch those numbers into your calculator, and you end up with 106.78. But take a look at the decimal places. If you look at 83.5, the 0.5 is in the tenths place, whereas in 23.28, the rightmost digit is in the 100th place. Well, take a look at the rule again. It says the answer has to have the same number of decimal places as there are in the measurement with the fewest decimal places. And so since 83.5 only has 1 decimal place, so it's expressed to the tenths place, we can only express our final answer to 1 decimal place, or in this case, the tenths place. And so we round 106.78 to 106.8 milliliters. The same thing applies for subtraction. We have 865.9, subtract 2.8121. We punch that in our calculator and we get this big number, 863.0879. But again, the first number, 865.9, only has 1 decimal place, whereas the second number has a total of 4 decimal places. And therefore, we can only report our final answer to 1 decimal place. You probably noticed that in some of the last examples we did some rounding, and here are the rules for rounding off numbers. It says here that if the digit to be removed is equal to 5 or more, so that means 5, 6, 7, 8, 9, then the preceding number is going to increase by 1. So if we have the number 5.379 and we want to drop the 9 so that we only have 3 significant figures, since 9 is greater than 5, we're going to round the 7 up to an 8, and we get 5.38 to express that number to 3 significant figures. If the digit removed is less than 5, so if it's 0, 1, 2, 3, 4, then the preceding number is going to be unchanged. So if I have this number here, 0.2413, and I want to express that to 3 significant figures, if I want to drop the 3, since 3 is less than 5, the number 1 is not going to change, and I end up with 0.241 and my 3 significant figures. Be sure to carry 2 or more additional significant figures through a multi-step calculation, and always do your rounding off at the final answer only. The measuring device you choose determines the number of significant figures you can obtain. Suppose an experiment requires a solution made by dissolving a solid in a liquid. You weigh the solid on an analytical balance and you obtain a mass with 5 significant figures, like shown here on the left. It would make sense to measure the liquid with a burette or a pipette, which measures volumes to more significant figures than a graduated cylinder. If you do choose the cylinder, you would have to round off more digits, and some certainty you attained for the mass value would be wasted or lost. With experience, you'll choose a measuring device based on the number of significant figures you need in your final answer. And so what I'm saying is that if the scientist measured the solid to 5 significant figures, as is shown here, and then they want to dilute that and they choose a 100 ml graduated cylinder and they read the meniscus right here, that's the eyeball, okay? And you would read that to 1 digit past the smallest calibration. The smallest calibrations here are 1 milliliter, and so we would read that as being 68.2 milliliters. And so since this number only has 3 significant figures, when I do my calculation that involves both the volume and the mass, I would end up losing some of the significant figures that I gained from my balance, right? Because I only have 3 significant figures in my volume measurement. Exact numbers have no uncertainty associated with them. Some are part of a unit conversion. By definition, there are exactly 60 minutes in an hour, 1,000 micrograms in a milligram, and 2.54 centimeters in an inch. Other exact numbers result from actually counting items. There are exactly 3 coins in my hand, 26 letters in the English alphabet, and so forth. Therefore, unlike measured quantities, exact numbers do not limit the number of significant figures in a calculation. Essentially, we can say that exact numbers have an infinite number of significant figures. Let's take a look at a problem that involves significant figures, calculations, and rounding. It says, perform the following calculations and round each answer to the correct number of significant figures. And so we'll start with A. We have 16.3521 centimeters squared, and we're going to subtract 1.488 centimeters squared. So if I take 16.3521 and I subtract 1.448, I get 14.9041 in my calculator, but I'm only going to express that to 3 decimal places because I have 3 decimal places in this number and 4 decimal places in this number. You remember the rules for subtraction, that the answer can only contain the number of decimal places as the number with the fewest decimal places. And so we'll write down 14.904 centimeters squared, and then we're going to divide that by 7.085 centimeters, like that. So when we take centimeters squared and we divide it by centimeters, we end up with centimeters. And when we take 14.904 and divide that by 7.085, we end up with this big number in our calculator. It's 2.103599, so on and so forth. In fact, I'll write it down to too many significant figures. We get 2.103599, and then it keeps on going from there. But how many significant figures should there be in our final answer? Well, there should only be 4 because the numerator has a total of 5 significant figures, but the denominator has 4 significant figures. And so therefore, I'm going to be limited by the number with the fewest significant figures. And so my answer can only have 4 significant figures. And so I'm going to have to drop the 5. And since 5 is equal to 5, and since 5 is equal or greater than 5, it's actually equal to 5, I'm going to have to increase the number 3 by 1, and I end up with 2.104 centimeters, just like that. Let's try the next one. We have 4.80 times 10 to the power of 4 milligrams multiplied by this conversion factor, that 1 gram over 1,000 milligrams. So this is a conversion factor, so we can assume that the numbers here are exact numbers. There is exactly 1,000 milligrams in 1 gram. So we can assume that we have an infinite number of significant figures in this conversion factor. So the first thing we're going to do is we're going to solve the numerator. And when we do that, we end up with our milligrams canceling out, and we have 4.80 times 10 to the 4 divided by 1,000, and we actually end up with 48.0 grams for our numerator. Again, we're limited to the 3 significant figures that are in the mantissa in this number right here. And so we're going to divide that number by 11.55 centimeters cubed. And when you punch that into your calculator, let me do it, we have 48 divided by 11.55. You end up, wow, with this big number, 4.15584. And there's more, I'm not going to write it down, and we have grams per centimeter cubed, of course. But we have to round this number to 3 significant figures because we have 3 significant figures in the numerator and we have 4 significant figures in the denominator. But remember, now we're doing division. And the rule is that when we multiply or divide, the final answer can only have as many significant figures as the number with the least number of significant figures. And so that number is 3. And so we have 4.15, so we're going to have to drop the 5. Since 5 is equal to 5, we're going to have to change that to 4.16 grams per centimeter cubed. Before I end this video, I just want to say a little bit about precision, accuracy, and error. We use the words precision and accuracy interchangeably in our everyday speech, but for scientific measurements, they have distinct meanings. Precision refers to reproducibility, or how close measurements in a series are to each other. And accuracy refers to how close each measurement is to the actual value. Now you can see down here in the bottom left, I have a target, and you can see that somebody maybe shot an arrow at it or something, I don't know. But anyhow, you can see that the bullseye is here in the center, okay? The bullseye is in the center right there, okay? And you can see that the person missed the bullseye, and so they weren't very accurate, right? They weren't very close to the actual value. They weren't close to the actual bullseye. But all the measurements, all the shots are very close to each other. They're in a very close group. And so since the shots are all close to each other, we say that the shooter had high precision but low accuracy. What else? You can see that in the second one that the shooter was pretty close to the bullseye in all of the shots, but the shots are not grouped together. And so you would say that the points that you see here, the shots, have good accuracy or high accuracy, but they have low precision. And then finally, in this one here, you can see that the person nailed the bullseye just about every time. So you would say that those points, those shots, if you will, all have high accuracy and they have high precision. Now, the terms accuracy and precision are related to two widespread types of error: systematic and random error. Systematic error produces values that are either all higher or all lower than the actual value. This type of error is part of the experimental system, often caused by a faulty device or by a consistent mistake in taking a reading. Random error, in the absence of systematic error, produces values that are higher and lower than the actual value. Random error always occurs, but its size depends on the measurer's skill and the instrument's precision.